The resistance of blood flowing through artery can be calculated with this formula. R equals C, which is a constant, times by L over R to the 4. This formula is famous to Poiseuille's law, which in this formula L and R are the length and the radius of artery. And as I mentioned, C is a constant in this relation. C is the constant related to viscosity of blood. Find partial derivative of R with respect to L. Find partial derivative of R with respect to R, which is radius, and interpret each of them. So let us start. What is partial derivative of R with respect to L? For finding the partial derivative of this function with respect to L, attention, L is the variable. C and R at the time that you get derivative with respect to L is a constant. So this is similar to something like 5L over 2 to the 6 or 2 to the 4. These are constant. What is the derivative of L? 1. And just remains the coefficient. So what is the derivative of CL over R to the 4? Attention, between C and L over R to the 4 is multiplication. So you can consider it as CL over R to the 4. Its derivative would be C over R to the 4. But we want to interpret this. Whenever we are finding any derivative, interpretation for that is rate of change. So what is the interpretation for partial derivative of R with respect to L? This is rate of change. But rate of change of what? Rate of change of the function. In this case, the R shows what? Shows the resistance of blood flowing through artery. So rate of change of resistance of the blood flowing through artery with respect to rate of change of resistance with respect to the variable that is in the denominator. In this case, we are taking the partial derivative with respect to L. So with respect to length of artery is this expression. C over R to the 4. So this is the interpretation for partial derivative of R with respect to L. And of course, this interpretation is when we consider the other terms as a constant. So radius we consider at that moment constant, and C is totally constant. Now let's find the other partial derivative. Partial derivative of R with respect to R. For this we have to use quotient rule because the variable R is in the denominator. Partial derivative of R with respect to R. Or the other way is to write this formula in the form of C L R to the negative 4. If you write this formula in this form, you don't need to use any quotient. Simply bring the exponent to the front, subtract the power by 1, use the power rule. Or you can use quotient rule. It's completely up to you. But I prefer to rewrite the function in this form and use the power rule. Then the derivative would be negative 4. We bring the power down. So negative 4, of course. C L times R to the negative 5. And it's better to rewrite this in the form of negative 4CL all over R to the 5. We bring back the R to the 5 to the denominator because its power right now is negative. Bring it back to the denominator and write it in this form. Now we want to interpret this result. Again, similar to the previous one. This shows rate of change of resistance of blood flowing through artery with respect to this time, because we take derivative with respect to R, with respect to radius of artery. This is the interpretation for this derivative. Can be calculated from this formula. This is the interpretation of this. And if you wonder why we got a negative in this formula, the negative shows that resistance decreases because it's negative. So resistance decreases when radius of the artery increases, which makes sense. If the radius increases, the blood pressures, resistance of blood flowing through artery decreases. So it completely makes sense. But for the length, it was opposite. It was positive. If you look at first partial derivative with respect to L, it was positive. I hope you like this video. If you like this video, please subscribe to my channel and see you in the next videos.